In this lecture, we're going to start where we stopped in the previous lecture with the geodesic equation with this extra term on the right-hand side. And we understood that that term could be traced to the idea that we are allowing the parallel transport of tangent vectors to actually be pointing in the same direction but a different magnitude. And by the way, what that means is that if I have the vector components A mu, and which by the way is just A0, A1, A2, and A3, if I take that and multiply by a constant say little a, then I'm dealing with the vector whose components are all a times the components of the previous vector. So all the components are multiplied by the same amount, and that same amount is what this c is. And you can see this is true for each of the different index values. So now the question is, we're going to now talk, we've already we were assuming that this parameter, this curve, gamma of lambda, is parameterized by this parameter lambda. And lambda, as it's metered out from lambda 0 at this point here, I guess that point is delta lambda 0, and as it gets metered out to, say, lambda 1, the place on the curve that we're positioned, or gamma of lambda, this mapping here will be gamma of lambda. Let me erase this, it's in the way. This mapping, gamma of lambda, moves from here to this point and then beyond, and it does so at a certain rate, and that rate is entirely determined by this function. But I can easily imagine creating another parameter, a different parameter, say sigma. And at sigma 0, we have say it's I guess what we're going to now, sigma goes from sigma 0 to, it has a value of sigma 1. Let me put sigma 1 here, and I can create gamma of sigma, and gamma of sigma will march along our curve, but at a different rate, as long as sigma is not 1-to-1 with gamma, as long as sigma does not equal gamma. But imagine, say, sigma is some constant times gamma. Say it's that a again, times lambda. So sigma is some constant times lambda. Then I know that gamma of sigma is simply gamma of a times lambda. And I can change gamma. I can somehow pull this a out and call this gamma prime of lambda. But I can also call it gamma of sigma just as well. The point is I'm reparameterizing it with sigma. But sigma could have any relationship with lambda. Sigma and lambda could have any relationship between each other. And the curve, once it's reparameterized, what happens is you move along the curve at a different rate relative to the parameter, which means that d gamma mu d lambda is different than d gamma mu d sigma. And these tangent vectors will all change. The tangent vectors will all change. And we're going to show that by reparameterizing this curve in a pretty clear way, we can always make this right-hand side equal to 0. And then that will ultimately be our geodesic equation. And that parameter will be called an affine parameter. An affine parameter. By the way, the relationship between an affine parameter and an arbitrary parameter is much more complicated than this. In fact, that's not going to cut it. You're not going to be able to do that for a general case. So let's study how to make the transformation between lambda and sigma such that we can eliminate the right-hand side of this expression. Okay, so here's our expression. And here I'm now going to write down the answer and then show you how that answer works. The answer is we're going to reparameterize this to the parameter sigma. And sigma, we need to know for every value of lambda. We know how this works for lambda, right? We know everything for lambda. So if I can tell you sigma as a function of lambda, then we can figure out how this works in terms of sigma. So I'm going to say that sigma as a function of lambda is going to equal this integral up to lambda of the exponential of the integral up to alpha of c times beta d beta, close the exponent, and then the outer integral is going to work on d alpha. So this is the expression that if I'm given an arbitrary, reasonably behaved lambda, and I have written down this equation, I can create a function of lambda defined exactly this way that will give me a parameter that I claim will eliminate this right-hand side. Now, the question is how did they figure this out? And it actually doesn't take too much thought to figure it out, but let's just presume a lot of people spent a lot of time and they ultimately looked at this and realized the reasonable thing that there should be something like this, and based on other reasoning, right? And this is what they found. And we just have to understand that this works. It's sort of a proof by demonstration, right? They've demonstrated, they want to prove that this can be parameterized in a new way such that this goes to 0, and they produced a parameterization that does it, and all we have left to do, our assignment right now, is to prove to ourselves that this parameterization does in fact solve the problem, meaning this parameterization works. Now, to get there, we need to know the fundamental theorem of calculus. It's ironic, this is going all the way back to elementary calculus, but it's the kind of elementary calculus most people have actually forgotten. So I'm going to do a quick review of the fundamental theorem of calculus, and then we will proceed to do the demonstration. First, a statement of the fundamental theorem that we're going to work with. We define a function, capital F, in this way. The value of capital F at the value of the independent variable x is equal to this integral of little f dt, where the upper limit of integration is x, and the lower limit is just some constant a. We can define this. As long as f is continuous on a certain interval that includes all of these pieces, then we can define this function as simply the value of this definite integral. The fundamental theorem of calculus tells us that the derivative of this function, evaluated at x, is simply equal to f evaluated at that upper limit of integration. That's the fundamental theorem of calculus. And it's important to go through it, so I will demonstrate the proof right now. If you already know this proof, just skip ahead a little bit. So we begin by just writing this down for two values of the upper limit of integration, x sub 1 and x sub 1 plus a small increment. So we're defining this function, right? Remember, everything above the line is sort of the definition of the theorem, and so we're defining, we're exploiting the definition of the theorem, or we're writing the definition of the theorem for two different circumstances, x1 and x1 plus delta x. I need a little sub 1 there. Then we combine everything in this way, where this is basically just an expression of the fact that an integral from a lower bound to an upper bound added to an integral from the upper bound to an even higher upper bound is just the integral from the lower bound to the higher upper bound. It's a fact of integration about how integrations are actually Riemann sums and how they can be summed together, and those limits all work out so that you can literally add integrals together, add definite integrals together, as long as their integrand is the same, and as long as their upper bounds match, you can combine them to form a single integral. And here, so this guy combined with this guy equals that guy. And so just rearranging that algebraically a little bit, I say, instead of saying this plus this equals that, I say that minus this equals this. And so now what I've done is I have an expression for an integral between x1 and x1 plus delta x1 in terms of f of x, this one here, f of x1 plus delta x1 and f of x1. And this, of course, is obviously going to be f of x1 plus delta x minus f of x1 equals, and let's see, I just leave the integral on this side alone, I guess, x1 plus delta x f t dt. Now, the mean value theorem tells us that this right-hand side, that there's some value out there, we'll call it c, is f of c times the difference between the upper and the lower bounds of integration, right? This is the mean value theorem for integrals. I won't be proving that one, but that difference is going to be x1 plus delta x minus x1, which equals f of c times delta x, with c is less than x1 plus delta x and greater than x1. Now with this in mind, we divide both sides of the equation by delta x plus delta x minus f of x1 divided by delta x, and that equals, there's some value of c that is going to equal to. Now, of course, we take the limit as delta x goes to 0, right? And that means this right-hand side becomes f prime of x1, and the left-hand side becomes the limit as delta x goes to 0 of f of c. I guess I erased the part where I said c is greater than x1 and less than x1 plus delta x. So because of this, as delta x goes to 0, ultimately c has to be equal to x1, so that's how you get f of x1. That's essentially called the squeeze theorem, in case you squeeze theorem. The squeeze theorem is that you're squeezing c between an upper limit and a lower limit that are converging, so c has to converge to those things as well. So the reason I went through this proof is basically I wanted to show that this a goes away. Notice that the difference between these two integrals is an integral that does not depend on a. And a vanishes by this step entirely when we rename these two integrals anyway. And the point being that that's why in this reparameterization expression you don't see lower limits here, because they know that you're really going to be using the fundamental theorem of calculus, and those lower limits don't even matter. And when you see integrals that don't have lower limits, that's a big hint that you're probably going to be exploiting the fundamental theorem in some way. Now, the initial expression of the fundamental theorem does have a, because I don't know exactly why everybody might choose to leave the a in there, but it certainly facilitates, the proof, you kind of need the a to show the proof, because this step here is a story about definite integrals, and definite integrals have an upper and lower bound. So you kind of need the a to describe the fundamental theorem of calculus, but when you use it, as we are about to in a moment, you don't need the a at all. You just need to know what the upper limit is, because the upper limit is critical, right? The upper limit is the value of what these things are. So, for example, the upper limit is it's the value of this function's derivative at the upper limit equals the value of this taken at the upper limit. So you definitely need to know what the upper limit is. Okay, so what do we do with this guy? And how do we show that this is going to be the reparameterization that we seek? Let's begin with that. Well, the first thing is I'm going to write d sigma d lambda. Now remember, all of these things are functions of lambda. So d sigma is a function of lambda, and that's the function. It's been given to us. And ultimately, when this thing is calculated, it's the derivative of a function of lambda, so it too is a function of lambda. But we usually don't write all of those dependencies down. We know that they're there. But that's a lot of the confusion in general relativity books and mathematical physics books, is that you've got to keep track of what's a function of what and where. And the shorthand sometimes, well, it always confused me. But anyway, so I'll write this down. D sigma of lambda evaluated at lambda, right? That equals the exponential of the integral up to alpha of c as a, let me clean that up, our function c of beta d beta. And why is that? Well, because of the fundamental theorem of calculus. We have a function on the left and an integral on the right side, integration with respect to alpha, and a function of alpha in the middle. So this guy here is playing the role of f alpha d alpha. I guess this guy and that guy is f alpha d alpha. And I have the integral from a to lambda of f alpha d alpha. So I've basically written sigma of lambda equals the integral from a to lambda f alpha d alpha. So this would be f of lambda from the actual definition that we used right here. So I've recreated this very structure where I've replaced that f is actually this function here. And this is a totally legit function. It's the exponential. This is a number, right? It's the exponential of a number. That number is some definite integral. And you can specify an arbitrary lower bound for that integral. And therefore, I now know that the derivative of this, or f prime, evaluated at lambda, is equal to this guy here, right? This guy here, evaluated at lambda. Oops, see, so that, this guy here, evaluated at lambda, that means I need the lambda right here, right? Because that's how you evaluate it at lambda. This guy is a function of alpha. That's how we know. This is the integrand. This is the independent variable is clearly alpha. The independent variable shows up as the upper limit of integration, so it's defined through an integration. Therefore, the derivative of it's continuous and on the interval and everything, as we assume that this is well behaved, right? So, in order to make this thing work, the left-hand side, the derivative of the left-hand side equals the integrand evaluated at x, which is the upper limit of integration. So that's how that alpha turns into a lambda. So now I have exponential of the integral from an arbitrary lower bound to lambda of c of beta d beta. So now I'm going to write, I'm just going to manipulate this a little bit. D sigma is going to be the exponential up to lambda of c beta d beta, that quantity times d lambda. So now I have an expression for d sigma, which will become very useful when I want to substitute for this, and this. And this, well, I substitute for all of them. So that, which will be our next step. Actually, the substitution I want to get at these things is this substitution, which is simply this expression which we just derived, where I divide both sides by the exponential term, right? That's where this negative sign comes from. Now I have d lambda, which I can literally substitute for each of these expressions up here. And let's execute that substitution. We will begin by substituting into this first part of the expression, the second derivative part. And we will write that as d squared gamma. Let's see, what letter am I using? Mu? D squared gamma mu d lambda squared is d by d lambda of d gamma mu d lambda. And now I'm going to substitute for these various d lambdas. I think I'm going to have to move to a new slide. So the first part of the substitution is this part right here. There's the second derivative. I break it up into its obvious decomposition of the derivative of the derivative. Then I leave that first derivative on the outside for now, and I'm going to substitute for this guy. I'm going to use this expression for the substitution. So wherever I see a d lambda, I'm going to replace it with this thing. Replace it with this thing. Notice there's a negative sign there. So when I replace d lambda, this d lambda with that object, I end up with the d sigma there, and the exponent goes into the numerator instead of lying in the denominator because I got rid of the negative sign of the exponent, right? So that changes, it makes it its reciprocal. So that is the first step of this expression. So this next step is simply an execution of the product rule. We're taking the derivative of the term in brackets, the derivative with respect to lambda. Well, we have a function of lambda here, and this is a function of, this is another expression that's just a function of sigma, actually, the way we've written it. It's d gamma of d sigma. We've made that substitution, but sigma is presumably a function of lambda. So this is a function of, we can take its derivative with respect to lambda, and we can take its derivative with respect to lambda. So it's a product rule. So this is the statement of the product rule where we're taking the derivative only of the thing in brackets, which is this exponential, multiplying it by the, whoops, good catch here, multiplying by this derivative, the derivative with respect to sigma of the curve, and then I take this piece and multiply it by the derivative with respect to lambda of the second factor, where this is the first factor and that's the second factor. So we're just expanding, we're just taking derivatives at this point, and we're just expanding using the product rule. Then the next step of this process is we execute this derivative. We're looking for the derivative with respect to lambda of this function. Well, any exponential function, its derivative is going to be the exponential function itself times the derivative of its argument. Well, the derivative of its argument is d by d lambda of the integral to lambda of c beta d beta. Well, that derivative by the fundamental theorem of calculus is c of lambda, right? Just, you got to work this rule, got to really work this rule to see that. I mean, well, you don't really have to work it, it's almost a literal restatement of it, just with c's instead of little f's and b's instead of x's, right? And lambda, well, b's instead of t's, and, well, what did I use? Yeah, b's instead of t's, and then lambda instead of x. So that is the derivative of the argument. So just using the chain rule, right, the derivative of the argument comes out in front, but the derivative of the exponential is the exponential repeated itself. Then, of course, you're multiplying by this factor up here, right, the part of held over from the product rule. Then moving on to this side, I make the substitution again for lambda, right, which substitution was that? That's this substitution for d lambda, so I get that in terms of d sigma. And so once I make that substitution, lambda becomes a sigma, and I get the second derivative here, but out in front I get another factor of this exponent in the denominator, a negative factor in the denominator, which I just lift to the numerator, and that gives me a 2 right there, right? So this is now this expression just expanded one step further. Now the next term we want to substitute for is this guy. We've just done the calculation for that. It was kind of a mess. You have an e to the 2 something and a lot of integrals and exponents and stuff, but that is the substitution for this guy. So now we need to substitute for these two in the second term of our expression. And those two we're going to make our substitution there. But this one is easy because we just are using this expression here 2 times, And so so you get two of these guys in the denominator, which pop to the numerator, and you lose the negative sign. So that gives us this expression right here, right there. So you see, and you can kind of see what's going to happen, right? Things are going to cancel like crazy, right? We've already got our C lambda has emerged, right? And clearly this thing and this thing are going to somehow get involved with each other, because that doesn't end up in the final picture. In fact, none of these exponentials end up in the final picture. So we can kind of expect a bunch of cancellations. But there's nothing like doing it. So we'll press on and finish. The last part, this last line here, is our substitution for the right-hand side, right? We're just, when I say substitution, I'm always talking about converting the d lambdas into d sigmas. So I'm substituting there, and the c lambda doesn't, the c lambda just changes right away to c sigma, right? We're just going to change that. Well, it stays c lambda. We're substituting for this guy here. And this exponential goes into the numerator, and it loses that minus sign, right? So that's what this expression is. So now we have to take this expression here, and I guess we add it to this one, and well, we have to multiply by this connection coefficient and add the two, and then that should equal this. And what we're expecting things to happen here is when we do all those substitutions, do this addition, we're expecting a lot of cancellation, so the right side will go to 0. These will all end up being sigmas. Okay, so well, how will that work? Okay, so this is what I get when I add those terms together. This is the first term, the term that comes from the second derivative, except that this lambda should be a sigma squared, right? And then I put back in the connection coefficient, and then this comes from the second term, which we just did, and then this is the right-hand side. But the good part is this right-hand side here, c lambda exponential times the derivative with respect to sigma of the curve, c lambda exponential derivative of the sigma respective curve. So that actually cancels. So already we've got our 0 that we're looking for. And then what we have is this exponential here doesn't really belong. But now that I have a 0 on this side, I just multiply by the inverse exponential. Remember, this is just some function. This is a function of like some arbitrary adjustment of the parameter, right? That c, right, was some kind of arbitrary description of how these vectors would change. The point is, it's a continuous and smooth function. There's no reason why it shouldn't have a nice invert reciprocal. It's never going to be 0 anywhere. It's an exponential, for God's sake, right? So those two, I guess red is wrong, because those two go to 1. Basically, I divide those two out, right? And I'm left with this plus this, right? If that goes to 1, that goes to 1, equals 0. And that's exactly the answer, right? It's d squared gamma mu over d sigma squared plus the connection coefficient alpha beta d gamma alpha d sigma d gamma beta d sigma equals 0. And that is the familiar geodesic equation, proving that if we start with any parameterization of a geodesic curve, that gives you this sort of sloppy right-hand side, because you don't demand that the parallel transport exactly mimic the tangent vectors. You just reparameterize the curve using this prescription. And by the way, you could actually, in principle, use this prescription to calculate a reparameterization if you had to. And you end up with the geodesic equation that we all know and love, right? By the way, I got to say that gamma, remember gamma, mu, alpha, beta, is a function of space-time. That always remains a function of space-time. But since you're on the curve, the function of space-time, it's really the only relevant points that are going to matter are gamma of lambda, right? Gamma of lambda, that is the curve that you're on. Those are the points in space-time. So when we reparameterize gamma, when we reparameterize the curve gamma, little gamma, the connection coefficient, which is also gamma, but capital gamma, that just gets reparameterized. That basically, it's getting the same space-time points, but it's just getting these space-time points, the ones parameterized by sigma. So in principle, there's no reason why I couldn't have written this as a function of lambda and then just simply reparameterized it as a function of sigma. It's going to be these are two actually different functions if you think of it in this term. If you think of it on this way, it's the same function. The connection coefficients are the same functions here and here. You're just feeding it a slightly different argument based on the parameter. But if you actually go all the way out to this side, these two connection coefficients are actually different functions because you've got to modify the function for the new parameter. But if you write it this way, you're not really writing it. This may be too in the weeds of a point. But the point I want to make is that this is a function of space-time, and as the function of space-time really doesn't change, it's just following the curve. You're feeding it different points at a different rate, and that's based on the reparameterization. Okay, so that's now the geodesic equation. We've demonstrated it in the mathematical terms of just the manifold, the manifold, the connection. So we're given a manifold, we're given a connection, and I guess our connection was mu. Let's see. The connection we used was mu alpha beta. We're given a manifold, we're given a connection, we're given a curve, and that curve has a parameterization lambda, and we've proven that we show what the geodesic equation is for arbitrary choices of these things. As long as the manifold is legit, as long as the connection is legit, as long as the curve is legit, any parameterization, we can create a geodesic equation. And we've also shown that we can always reparameterize it to get this geodesic equation. And this parameter, by the way, if you do that, if you have a parameter with this geodesic equation, it's called an affine parameter. And you should be able to show that if I have sigma as an affine parameter, if I take sigma, multiply it by a constant, and add a constant, I still have an affine parameter, right? So if I create a new parameter, rho, which is some constant times an affine parameter, sigma plus some constant, rho is also an affine parameter. And you can actually make this substitution, d rho equals a d sigma. You can make that substitution into here, and you can prove that for yourself. Okay, so next we'll move on to a different examination of the geodesic equation from a different angle.